First things first, send your homework X, but wait a minute. Homework X is only for replacing the one homework that you had it for 8 points. Okay? Don't send it to me if you want to replace a 2-pointer. You can keep it, and I'm glad you worked on it, but it's only for replacing 8-pointers. Send them to the aisles, please, and then you guys on the aisle, send them downhill. Yeah. Now, you can't replace your exam score with it, so sorry about that. Send it to the aisle, and then you guys on the aisle, send it on downhill. Okay. We got a few more coming downhill. Okay, just stack it up here. Okay, is there anybody else with homework X? Come on, you guys. Okay. All right. Oh, here comes some more homeworks. Thank you. One more set. Thank you. All right, let's get going. Shh, 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 shh. We got a lot of stuff to cover today. We're going to do a calculation of Bernoulli effect applied to the area of an airplane wing today, an airfoil. But before we do that, hey, are the fires of Sauron burning in Orange County or what? What's all that smoke from? Because I actually saw ash coming down and blowing around. Sauron, he's up to his tricks. Sauron rises again. All right. Shh, 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 shh. Have your clickers ready. All right, the Bernoulli effect. Here's a nice little quote from chapter 12.1. When a fluid flows into a When a fluid flows into a narrower channel, its speed increases. You know, you've seen it a million times. You don't even think about it. But the net work done increases the fluid's kinetic energy, and as a result, the pressure will drop in a rapidly moving fluid, whether or not the fluid is confined to a tube or not. And so in this case, the examples that they're talking about in the book are water, which is an incompressible fluid. And so here's a figure 12, or figure 2 from chapter 12.1. Just a kind of a generic looking pipe that narrows down. It has a little transition. to a narrower pipe. And the idea is that in the narrower channel or the narrower tube part of the tube, there's a faster speed. And the reason for that is if it doesn't have leaks, okay, then there's going to be no loss of mass. So mass is conserved, and also if it's also going to hold if it's not compressed. Now, if you have a compressible fluid like air, things are a little bit different. But for an incompressible fluid like water, which water can be compressed, but not by much and not under most circumstances. When that's the case, this is what we call the continuity condition. The ratio of the two areas, the big over the little, is inverse to the proportion of the speed of the big versus over the speed of the little in the little part of the tube. So it's A1 over A2 equals V2 over V1. And all that means basically is that the area times V2, area 1 times V1 is equal to area 2 times V2. And if you think about it, what that means is the air, the amount of water going through per second is basically the area times how much it flows in 1 second. So that's basically V. So the volume per second is just the area times the speed. And if you haven't lost any mass and if you haven't compressed it, then this will hold. You came in late with homework. Who came in late with homework? Just pass it down the front. Pass it down the front. Just pass it downhill. The guys on the aisles have already had a big workout with homework, so just pass it straight downhill and let these jokers in the front seats deal with it. So for those of you that have an anatomical interest or are interested in anatomy class and so forth, just think capillary versus aorta. Aorta is this ginormous. Is that true that the aorta is the biggest artery in the body? Yeah. And then everything else branches off of that, basically. And then the capillary, of course, is the last level of vascular bodies. No, man, I want one of you slackers in the front row over here to do it. You guys, you or with the hat, you were supposed to carry. You were supposed to carry that over. That's -5 bonus points for you. And no brownies on final exam day for you, my friend. Okay. Just kidding. Anyways, we're good. It's no problem. All right, so in terms of anatomy, aorta versus capillary, that's a good comparison. And, I don't know if you guys that are heading for med school and whatnot, I don't know what the result of that is, the different, going from aorta to a small, because your blood's going to go faster, right? Because your blood pressure is relatively even throughout the whole system. But in terms of, what blood is there to do, I don't know if makes it better if it's faster or not, because it's got all these ions and leukocytes and all that kind of jazz in it. But I do know about this. This is at a place up in New Hampshire, the Pemigewassett River, up in the White Mountains. And my wonderful students, if you've never been outside the state of Florida, there are these things called mountains and streams of water. And in the summer, I've swum in this place. It is it's got little chutes where the water is. It's just the right size for a human. It was carved out by glaciers and stuff. But, yeah, there's all kind. And so you go through these sluices and then you go off into a pool of water. And on a hot day, oh my goodness. But there's nothing like this in Florida, so you got to go up north to see stuff like that, or maybe even Virginia probably. Question? Yes, the entire list of every mountain in the northern hemisphere for your final. Everybody else, just, North America. No, it's an advanced concept for you folks from Florida. I know, but, anyways, let's talk about the Bernoulli effect. Bernoulli's equation is a form of conservation of energy principle, basically. Um, and the author makes this note in chapter 12.2. Note that pressure, P, has units of energy per unit volume, too. Every term in Bernoulli's equation, which will float out here in a second, has units of joules per cubic meter. And that's actually kind of important in the theory of relativity as well. I mean, you know what's interesting? In the Big Bang Theory, we model the entire universe, all the matter in the universe as a fluid. And it will obey something like the Bernoulli equation. And it has certain dynamics and stuff. And from that, we can derive, all the properties of or most of the properties of the Big Bang Theory as the universe expands from from the moment of the Big Bang. But anyways, energy per unit volume, pressure. Yeah. So it's a full description: pressure, velocity, and position. All right. The continuity equation or the continuity condition is a little bit limited in that it doesn't permit for different densities. It's basically something that you hold. Now, versions of that hold. Let me pot this down a little bit. This is a little hot. Versions of the continuity equation hold for compressible fluids, but it's beyond the scope of this class to go into that much detail. All right, so the Bernoulli equation, here it is, basically re-encodes conservation of energy. And if you're in the surface of the sun and you have all kinds of electromagnetic interactions in that plasma of separated nuclei, ions and electrons floating around, and positive ions going one way and electrons going exactly the opposite way and doing it faster, you get a lot of chaos. And the fluid equations, magnetohydrodynamics in the surface of the SUN are the hardest thing to do in physics. And second of all, and then relativity is second probably. Anyway, so this is the Bernoulli. And when we say that it's a constant, what that means is if you calculate pressure, density, V squared, and H at each little pixel of fluid flowing through your system, they're all going to be the same. It's going to be some constant, okay, until you go over a waterfall or whatnot. Right now, an example of Bernoulli's equation is this: if you have a region where there's a high velocity, like between this truck and this vehicle, then that's going a little bit faster there in the middle. You're going to have low pressure in there. So out here, where the air is streaming by at normal speed, whatever this, if it's still air and you're going 50, then the velocity of those streamlines is 50 miles an hour. Okay. Now in between, because you're squeezing the air into a smaller channel there, you're going to have a little bit more velocity. Therefore, the pressure is going to be a little bit smaller. So down in here, high speed and low pressure. And for that reason, you get a little bit of squeeze between the truck and the car. And you may have felt that. Sometimes when I'm stopped on 436, making a left turn, like where my old apartment used to be, and sometimes you got to wait. And so waiting, all the people going past you, you're in the turn lane, you're waiting, and all the people are, going like mad on 436. And even little cars will cause my vehicle, my Jeep, my Cherokee, to shake a little. And that's from this. That's from this. It's the Bernoulli effect. It's basically causing both vehicles to squeeze together just a little bit. And you're set in one place, So you notice it. You're gonna, you know, you're stopped to go left, so your car's going to go like this a little bit, and you'll feel it. But that's what that is. All right. Now, the authors have this lovely phrase here. The airplane wing is a beautiful example of Bernoulli's principle in action. And I humbly agree with that sentiment. And for that reason, we're going to do in a few minutes a calculation together, and I'll get you started on .cam with it, of the pressure differential and the net force on an airplane wing. Now, the airplane wing that I chose is Mr. F-16. And here's a picture of a perfectly good airplane called an F-16, fully loaded. And you know those guys, they train hard, but for some reason, they bring their cell phones up in the cockpit and they get selfies a lot. Now, this guy's from, this is the Dutch Air Force training. Here's a guy from Turkey, the Turkish Air Force, all these NATO Air Forces. I don't know. Of course, here's the little buddy, Mr. AIM-9 Sidewinder. This is the Danish, the Royal Danish Air Force. Anyway, so we're going to do an example here with Mr. F-16. So let's go ahead and make some notes. And what we're going to do is we're going to take an F-16 in level flight. So unlike this guy, here's another selfie. Although I'm not sure that this is not photoshopped. Does it look photoshopped? Have you ever? Well, I know they do this missing man formation and stuff down, you know, at football games and, you know, funerals and whatnot. So it's normal, but I don't know if that's actually a selfie from, because you can't see the fuselage. I mean, you can't see the cockpit canopy. You know, these other ones, look at these other ones back here. See, look at the distortions in the glass above this guy. And here you can actually see the reflections in the, you know, so you can actually see a little bit inside the cockpit. So I don't know if this one was photoshopped or not, but still it's pretty cool. So let's take it in level flight. And we're going to use Bernoulli equation. And the wing area for one of the wings is about 24.0 square meters. I looked that up, okay? And it's not exact, but we'll use this as a typical wing of an F. So this is the Bumblebee variant with exactly 24.0 square meters. So this is Bumblebee's F-16. All right, airspeed above the wing, a little bit higher, 251. Below the wing, 225 meters per second. So they're both up in the area of, you know, these numbers might be a little bit fakey because I don't know that the difference in the velocities is that big. But let's work with these numbers. 251 meters per second, that's about 500 miles per hour. 225 is about 4 something miles per hour. So that's normal for an F-16. Definitely easy as a walk in the park for Mr. F-16. All right. Now here's a diagram from chapter 12, and actually this also shows a sailboat. So over here to the left is an airfoil. Let me get my cursor over here. So here's your airfoil. Side view of an airplane wing. Now that's the side view of the airplane wing of the Wright brothers flyer. They made it look like a bird's wing with this particular profile. A modern jet is not going to look exactly like that. You know, a prop plane, you know, like a Cessna might look a little bit like this. But anyways, this is the one that we'll work with. It's just a diagram. So the idea is that the fluid has to move a little bit further in the same amount of time up here across the top, and because of this bump. And so therefore this stuff down here is slower, high pressure, faster, low pressure, pressure differential, upward. Therefore dynamic lift. So all you have to do is figure out your pressure differential and then the area of your wing, and you're good. All right, now over here, something similar. And this is an overhead view of a sailboat. And here's a sail, and they're heading upwind pretty good, but they're still getting some thrust. The wind's going through like this, depositing a little bit. So it's not the impact of the air molecules, it's the pressure differential. Okay, so it's going a little bit slower over here, or excuse me, a little bit faster over here on the lee side of the sail, and on the windward side of the sail, it's a little bit faster. So low pressure here, high pressure here. Net force perpendicular to the container. In other words, the shape of the wing. And as I understand it, the people that design sails for these racing yachts like the America's Cup, they spend an awful lot of time on the aerodynamics of those sails. And I could believe it looking at this picture. And I've sailed in boat, I've taken small boats and big boats out on the ocean. And that's what you got to do. So anyways, that's an extra picture of showing dynamic lift, or in this case, dynamic, pressure helping the boat to rotate. Now, the way that you do this, the way that you apply Bernoulli's equation is you take a pair of pixels. So these two yellow babies up here, a little pixel of fluid, and you just follow it through its motion. And at every step of its motion, you recompute P plus 1/2 rho V squared plus 1/2 rho GH, or 1/2 rho GY if you want. And that's going to be a constant all along that streamline. Right? So that allows you to figure out from the pressure and the ambient density of the air and stuff, what the pressure is, and then you can get a pressure differential, and then you get a net upward force if you're going fast enough. All right, so that's what we try to do with these things. So now the ambient air density is in the equation. That's the rho here. Okay, so we're going to use 1.29 1.29 kilograms per cubic meter. Now remember that the density of water is 1,000 kilograms per cubic meter. So this is a lot smaller density than the density of water. This is air. Okay, and air is compressible, but we're still going to use the Bernoulli equation in this. Now we're going to ignore the ambient air pressure. And why do we do that? We're just going to, in other words, we're going to compare and calculate a pressure differential. So the ambient air pressure, aside from the fact that the lowering of the pressure versus the increasing of the pressure below the wing versus lowering of the pressure above the wing, that's really what we're caring about. So if you're up at 10,000 feet, or if you're at sea level, or somewhere in between, whatever the air pressure is there, what really matters is, that's in the pressure, but it's going to subtract out because we're taking a pressure gradient. We're taking a pressure differential. So we're going to subtract pressure on top from pressure on the bottom, and hopefully that's a positive number, which means we have a positive upward pressure. And so whatever the ambient air pressure is that day, 1,002 millibars or whatever it happens to be, that'll subtract out. All right, so we don't have to worry about that. Now, there's another term here that we have to deal with, and that's rho GH. Here's a question: can we ignore it? Do we have to calculate rho GH? Do we have to make that a difference? Because there's an H differential. There's a positional differential here. The rho is not going to change, G is not going to change, but the vertical position is going to be different. So let's do a little side calculation before we get to the main calculation. Let's estimate the wing thickness of an F-16 at 0.80. Now those wings taper, and I'm not sure that it's a full meter wide or a full meter thick at its thickest point, but let's say 0.80 meters for a typical thickness of an airplane wing for the Bumblebee F-16 that we're working with. All right, now, if you go pixel by pixel, a pixel on top, a pixel on the bottom, and calculate rho GH, here's what you got. You have rho g times the y coordinate up on top, and then rho gy times the y coordinate on the bottom. Now again, what we want is the differential, the delta. So really, what we have to calculate is rho g times yt minus yb, or minus yb. So that's the difference in height, and that's 0.80 meters, by my assumption. Now, if you want to calculate, make an ultra precise calculation of the lift for a square meter of wing surface out by the tip, where it's only this thick, you could do that. That's about 10 centimeters maybe, okay? But if you're in closer to the root of the wing, you're talking maybe a little bit closer to a meter. But so we'll use this as our differential. Question? We're not using negative 9.8. And the reason we're not using negative 9.8 is because this is a pressure situation. Pressure, basically we're working with pressures here. And pressure is isotropic. There's no directionality. Pressure is not a vector quantity. It is the sum, it's like the energy density of the sum of all the delta P over delta T interactions that your fluid has with its container, if it has a container. But you still calculate it, that's still the pressure, even if you're, if you're in the atmosphere, which really doesn't have a container. It has basically the surface of the earth, and the space is not a containment for it. But it's isotropic, so you don't have a direction to it. And so G, we're just going to use the magnitude of G in this equation. And again, on this one, we have a little bit of directionality to deal with in terms of above the wing and below the wing, but we're taking care of that in this case here. Now, if you multiply this all out, you get 10.1 joules per cubic meter. All right, now let's keep that in our back pocket. If we need to deal with it, we'll deal with it. But let's calculate the other terms and see how big they are in relation to this. And if they're really big in joules per cubic meter, then we'll be justified in just, forgetting about this baby. So this will be a drop in the ocean, spit in the bucket type of a thing. All right, now we're going to go to the document cam. Let me pause the YouTube. And we're going to work on the document cam. Come on, baby.